And next, we're going to talk about evaluation functions a little bit.
So evaluation functions basically scores any non-terminal states in a depth-limited search. So basically, they only are relevant because we have to cut the search at some predetermined depth. So the ideal function should return the actual minimax value of the position. But in practice, we usually use a weighted linear sum of features that approximate the actual minimax value in some ways. Yeah. For example, one of the features for the game of chess could be the number of white queens minus the number of black queens, etc., etc.
Mm-hmm. Yeah, let's take a look at some Pac-Man examples, and let's consider whether certain states will be good or bad with a good evaluation function. So what about this state? We'll say it's pretty good since the ghosts are pretty far. What about this one?
Probably less good because the ghosts are like right next to Pac-Man, right?
Yep.
What about here?
It's kind of similar to the last configuration, I'd say. What about here?
I think the Pac-Man is in a very bad position right here because basically it has to rely on the ghosts being very suboptimal and moving out of the way. Otherwise, the Pac-Man couldn't make any progress and they would just get eaten.
Yeah, right here.
Okay, yeah. Now the Pac-Man is really screwed. All right, so let's see an example of interesting behavior that arise from shared utility functions in minimax formulations. So basically, in this video, we'll have two ghosts and then a Pac-Man, and let's see what are they going to do. All right.
So basically, the two ghosts are both minimizers that share the evaluation function and utilities.
Yeah. All right.
Finally.
Yeah. As we can see here, even though the two ghosts doesn't actually communicate strategy with each other because they're minimizing the same utility function, they're able to form a coordination strategy. Yeah. By basically one going to the top and one going to the bottom, cornering the Pac-Man and capturing it.
Evaluation functions are always imperfect because if they were perfect, then everything will be optimal. And the deeper the tree evaluation function is buried, the less quality of the evaluation function matters. So if you can actually go down to very deep in the tree, your evaluation function can probably be like a little worse, and you'll still do fine. For example, if you can almost go to the end of game at chess, your evaluation function might just be, okay, am I winning or am I losing? And this is another important example of the trade-off between the complexity of features and the complexity of computation. So this happened in search when we try to come up with a very good heuristic function. There's a trade-off there because sometimes a perfect heuristic function is very expensive to calculate, whereas you could use the computational resource to do the search or planning instead.
All right, so let's take a look at another demo.
So here's a configuration. Let's think about this for a second. We'd like to eat that dot. And if we look forward just a couple steps, right, we won't be able to see the actual eating of the dot or any future collisions with the ghosts. We're just going to look forward and see whether or not we can be closer or farther from the dot. But we'll have to have an evaluation function that says being close to the dot is better than being farther, or it's all going to look the same to the evaluation function. So let's see what happens when we search 2 ahead. Well, we're going to move towards the dot, unsurprisingly. Except now what happens? We get pinned.
Yeah, so basically, if you're only depth 2, Pac-Man will only know, okay, I have to go to eat the dot, so I'm just going to move forward. If you actually take a closer look at the configuration in the next example,
what happens if instead we have a mastermind Pac-Man here and we can see all the way into the future? We can see the whole game play out, which on this board is feasible. Well, now what should we do? The critical thing is that blue ghost is going to go somewhere. And once it goes somewhere, it's committed. So what we should actually do, and this is not obvious from a horizon of 2, is move towards the orange ghost, because we're still not actually in any danger. A reasonable evaluation function that looks just a little bit in the future would say, that's crazy, you move towards the ghost and away from the dot. But in fact, if you look deeply enough into the tree, you see that what this allows you to do is force the blue ghost to make a decision before you have to, and that lets you get around.
So that's why depth might matter in your search tree. And last, we're going to talk about the synergy between evaluation function and alpha beta, basically 2 techniques that we use to overcome the resource limit.
So, so basically, in alpha beta pruning, the amount of pruning depends on the expansion ordering. So basically, a good evaluation function can provide, some kind of directions in terms of expanding the most promising node first, and which later makes it more likely that a good alternative is already somewhere along the path, before reaching there, and we were able to do more pruning.
And the second part is basically a rehash of what we talked about and how we motivate alpha beta pruning. So essentially, if you're at a min node, that value is only going to keep going down. And once that min node value get lower than the best option for max along the route, you can basically ignore all of the rest, because the max node are not going to bother looking at that min node.
Yeah, so that's why if evaluation function provides upper bounds on the min value, then the upper bound already is lower than the better option along the path, then we can actually prune.
Yeah, so you can basically combine the ideas of the 2 and use the evaluation to help with alpha beta pruning.
All right, I think that's all we have for this one. Next time we're going to talk about uncertainties in in terms of the opponent's behavior, and what are we going to do there when we mix probability into this whole business, because everything we talked about so far is deterministic.
All right, see you next time.